Hello, good afternoon, all of you. Am I audible? Good afternoon, all of you. Today is second day of our FDP. We arranged our institute, Dr. Babaji Sawanke Institute of Engineering and Technology. And from yesterday, hello. Today I welcome all the participants. Today is the second day of our FDP. I just request our resource person to address all the participants. So please start your session.
Okay, ma'am. Good afternoon to all. My name is Manthan. Today we will start our second day of FDP. I'll start to share my screen right now. Is my screen visible to all?
Yes, sir.
Yes. Can you see my screen? Okay. So the thing I want to start with is yesterday for our first session, do you have any sorts of doubts in solar or any type of doubt in the introductory part yesterday we had? Okay, so let me start while showing you some of the images of our existing solar system. So this is what a 240 kilowatt solar system looks like. So these are some of the images of our college area where we have installed 240 kilowatt, which generates 1000 to 1200 units per day. So it depends upon the solar intensity which is available. So this is the old photograph. If we see the new, when I'll get the new photograph, there will be some panels installed on this side. Or you will see all these gaps covered. So this gap we have put it up for maintenance purpose. We have a small ladder over here so that we can go upstairs. We can have all the maintenance of both the panels. If you see properly this design, so this panel has 9 panels on the top, 9 panels in the bottom. Okay, so we have designed it specifically so that a single person having a 3-meter rope, 3-meter wiping rod can easily wipe the panels from upper side and also from the lower side. As we have this type of roof, so there was no need to have a special walkway design here. Okay, so we haven't done it. And also later on we have made this is an old photo while installing. So later on we have made handrails and everything this side. Okay, so this roof togetherly contributes to 120 kilowatt. This way, this is the A wing. This togetherly contributes to contributes to 120 kilowatt of each. So how will you calculate 120 kilowatt? If you say is of 315 or 335 kilowatt. Okay, 335 kilowatt. So if you divide 335 kilowatt, you will have the proper number of solar panels installed on the roof. It will come almost up to 300 plus. 300 will be 100 kilowatt and 40. So 620 will be the number of panels installed on solar for 120 kilowatts. So each panel will be almost of 335 watt. Okay, so what we do later on when I'll show you an image of inverter, This is an on-grid inverter which you are looking. So this inverter is generating 110 kilowatt. Okay, the solar inverter is of Growatt company. So it has its own specifications. The upper limit, if you see, is of 110 kilowatts, and the later strings which we have attached. This is the DC side, and here you have an 185 square which is the output of the inverter. You see a small cable coming. This is the data cable which we were using as a zero export function. So we were independently running the almost half of the solar plant while we were in of the solar plant for college. So this used to be a data cable which used to inform the inverter for the current load, and inverter used to send the proper ample amount of current which can run the solar full college. Okay, so this is the DC side where each let's say from this image the total 9 panels and 9 panels, the togetherly series connected panels. Okay, all these panels are interconnected in a series format. In this way, you have a positive terminal this side, you have a negative terminal this side. This togetherly stacks up. You see a small wire here, right? This is a heavy wire, so this contributes to a single table. This is a second table, third table. Let's say this is one string, second string, third string. This together, all strings, they combine and get together at the point here. Okay, so you have the string number marked here. Later on, this come through this DCDB. This is a DCDB box which simply has a simple fuse of 12 amps, which is the maximum current. When you connect 18 panels into series, so each panel has 3 volts and 9 ampere of current. So connecting them in series will result into 620 volts total voltage, and 9 amps will. Okay, so you have a 20 MPPT based solar inverter. Okay, on the DC side, so each string will have an input 100 volts and 9 amps current. If you speak about the wire, it will be of almost 4 square solar DC wire. Specifically, I'm using wire for such a reason that this wire is based of pure copper and it has less resistance. So when a wire will have more, what will happen as the voltage levels are high, the wire, there are some chances of wire getting heated up. Okay, for this reason, the connected with the solar panels are also a DC of a solar wire, so that they do not heat up a lot more. The next thing you see, this is the ACDB. ACDB is nothing but AC distribution box. So it has its own indicators. You can see your solar ACDB panel. Okay, this connects. This is the adjacent panel with solar system. After once the AC output is generated, panels, the three-phase supply 440 volts and almost 167 amps current. It flows through these wires. It comes into DCDB. Track your generation. You have an earth fault relay. If there is some earthing relation or grounding happens into wire, so this the connection stops. You have a 440 40 kVA switch which has trip indication, MCCB off condition and MCCB on condition. So all the safety features related to AC side and the needed safety features for our whole electrical system. So it is being connected into this ACDB box. So after this ACDB box, all these connections are moved toward the main metering LT panel, where you have your MSCDCL incoming connection. So you connect this solar connection parallelly to the incoming MSCDCL connection, and when you connect the same connection to the MSCDCL connection, inverter verifies whatever frequency is coming, whatever are the wavelengths for sine and cos, all these wavelengths, and then the same wavelengths are generated, are calibrated by the inverter, and then we are ready to export the power into grid. So this is the basic connection of the solar inverter. You have a 110, 120 kilowatt inverter here. You have its own ACDB and the heavy wire. This is 185 square mm wire. We have yesterday, as I spoken, we have two inverters. One inverter is 110 kilowatts. Another inverter is in the another wing. Okay. So another inverter is in another wing. So this is the input terminal for inverter 1. This will be the outgoing terminal, and another one cable which we have entered later is this is the chamber for one inverter, for another inverter, and this is the main safety feature device. So we have a simple connection made up of it, made up here, and this 185 square mm and through for a temporary basis it was directly laid. Later on we have a proper tray for it, and then we have taken it directly to room or generation meter room, or else let's say LT panel room. Okay. The main thing while installing the solar panels on the roof is how you design the solar panels, in what way you do it. Okay. So while stacking the panels, you have to properly see the lower ground surface, whatever angle you have. In terms of our condition, we almost had 19.6 degrees of solar angle available, so we need to worry. Only the upper edge of the solar panel, while fixing, we have increased it to 1 inch, so that proper we get a 20-degree angle, and we have installed 670 panels for a total consideration of 240 kilowatt. So this is the almost say this is the chemical engineering branch of our college. This is the first year department of our college, and this is the academics and everything section going on in the ahead of the college. Okay, so this is what a 240 kilowatt looks like. Now if we come on to our 3D design, what we have done earlier. This is how the design looks like in 3D. Are there some new members who have joined today and those who were absent for yesterday's lecture? No, good. So everybody from yesterday is present today. Okay, so if you see here gap over, so this is system defined, but you can, of course, you can calibrate, you can change these gaps from the solar panels. You can have an handrail. So this is what a 3D design for our college looks like. This is an identical, the photograph which you have seen has been taken from this roof. No chances of getting the last roof photographs unless and until we have a drone. Okay, so that drone photography also I am not having currently, but I'll show you on a group also. So today what we'll do, today we will have, we will from scratch, we will try to design an optimal design. Okay, any of the building you can later take this version for demo purpose and you can try this thing. Now I'll go to the dashboard section, and we are having a project going on for 250 kilowatt. This is for guest house of our Garda Chemicals Limited. Okay, there are several buildings you see here. Yes, so this is the overall look of the Garda Chemicals guest house, you can say, or a staff quarters, you can say. So this is the main road coming to the Garda Chemicals. This is the main entrance of the Garda Chemicals. You have 1, 2, 3, 4, 5, 6, 7, 9, 10, 11. Total 11 buildings which will be converted to solar in couple of months. Okay, so basically BHK flats. These are 2 BHK flats. There is also an hostel. Okay, for the single working staff. You can see this is the, so this is another building. This is the open ground you have the generator meter room, or let's say the main powerhouse, where the power comes is these trees. Okay, and these are some more buildings attached. So one thing you can see is these are flat roofed panels. Okay, these are flat roof panels. These buildings have somewhat slope, but this is a flat slope where you can install solar panels. This is also a shed type of thing. Okay, and these are some of the roof. Let's say this roof has a down angle at this side, and again a down angle on the other side, and again you have this type of obstruction in between. So we have not so interested on putting, and also we have a lot more trees aside. So we have neglected both these two buildings. Okay, and we are ready to install such type of solar thing on all the other available roofs. If you wish to see it in a 3D view, so this is how the total Garda Chemicals colony looks like. Okay, so here you will see solar panels fitted on in different angles. Okay, actually the north and south direction, if you see, so at the north hand side you must have the uppermost part of the solar panels. The top part must be this way and south must be down. But the thing is, the topography is such as the trees at the building, you have these things, and you can our task is to attach almost 240 kilowatt for the Garda Chemicals space available. So one thing is we can do it roof mounted, and we almost have this area. Okay, this area which is actually covered in trees, so we can clear it, have a proper 200 kilowatt ground mounted structure installed on this area. The one trustees and our MDs there, we don't have the permission to cut the trees, because you see this is the residential area and completely covered with trees. We physically visit this place, this is almost like an forest type of area, and clearly they have maintained each tree, they have maintained the pathway, they have maintained solar street lights, they have maintained the garden grass, and everything is almost up to the mark. So getting the permission for a ground mounted thing, first attempt or first try is to have the solar access for roof purpose. So while designing such system for so many buildings, there is one task that we can independently calculate the energy demand for each building and attempt to generate so much of electricity at its same roof, and use a micro inverter and fulfill the energy requirement then and there itself. But the thing is, it is not so far available, so we are trying to utilize at most the maximum area whichever roofs we are having, it will be optimally used, and also we will have a lot more space there, and we can almost to the smaller roofs or smaller buildings which we have. Normally 1 RK or 1 BHK buildings have almost an area close to 300 square feet or less than 500 square feet. So the total building area will be also almost 1000 by 1000 square feet. So to generate almost the power for four roof buildings, the power daily almost it is almost of 30 to 40 units, and to generate 30 to 40 units you will have approximately the solar be 13 to 14 kilowatt. So required space for 13 to 14 kilowatt is, so what we'll do is try to attempt have a solar on this type of roofs available space. We can also attempt to have an optimal generation here. I'll delete the available model here. This is basically the canteen area, which has almost a proper aligned shed. Okay, but the direction is not so far useful for us. But the east slope side we can use almost and all the east facing sides we can use, so that we can have an optimal generation. We also have some of the obstructions, but these obstructions are almost of 1 feet, so it doesn't matter so far for us. So while designing, first thing we have to design is the roof, how it is available. So first thing we know is this is a shed type of thing. So we will select the pitched roof option, and also we will select the available roof space. You can also zoom in and select the area. So this is what a simple pitched roof looks like. But the thing is, we have to convert, we have to change this side to, we have to increase the length, we have to decrease this side. And we have to change the base height up to 15 meters. This height represents the height of the building from base. And actually the tilt is almost, it is 20 degrees. So if we 3D view, you will have a proper roof like this. Okay. So the second thing we can do is, I'll come to 2D view again. So far, if you see in the total plant, we have attempted to install almost 120 kilowatt. You can see here 120 kilowatt we have installed on various roofs available. So our task is to add another 8 so that we can reach 200 kilowatt, and then we can optimize each solar panel to, let's say, 720 watt, 550 watt, and easily gain 250 kilowatt on this solar roof, on the available space or all these solar roofs. The thing is, this software allows up to 200 kilowatt of solar design. So you can almost design 200 kilowatt. 200 kilowatt is the upper limit for this software. So up to then you have to have another design designed for 50 kilowatt, and this design will show up to 200. Okay, so the thing is, if I select this panel, go into its subarray, you will see this panel is of 315 watts to 550, 440 watts. Nowadays, you can say that almost solar panels prices have dropped so far that you get for almost 13 to 14 rupees per watt. So 550 watt panels you will have at much cheaper rate from companies like Wari, let's say Adani, then Adani is also, then Tata Solar also there. So these companies have manufacturing, and they have automated the solar manufacturing so vast and so fast that you get the solar panels almost for 13 rupees per watt. So if we calculate the cost for solar panel, let's say 550 watts, so 13 into 550, it comes to 6,500 per panel, and I'll multiply it with 6 panels. So it will come to 3 kilowatt system, and the price will go up to 39,000, and 39,000 panel cost with GST. We can have a 3 kilowatt solar panel system. We can additionally add an solar inverter, let's say of Growatt. If we consider, then it will be up to 18 or 19,000 plus GST, which are two major parts of a solar system: solar panels and also the solar inverter. Structure based on the roof space available or the condition available at your comfortable space, it matters, but it almost let's say 18 to 19 rupees per panel. Let me see. So you can modify it as per your customization, as per the available space, and also as per the customization. For 6 panels, you can easily design a structure with almost 10 to 12 kgs of GI channels, box type channels, or C type channels. Easily with 10 to 12 kgs you can do. And another thing you will need is the safety features, let's say DC-DB box, AC-DB box, and wires. So it won't cost you more than 15,000 combinedly, and another 7,000 for the net meter, and 3 to 4,000 for the MSCDCL net metering process. Talking about on-grid system. So togetherly, a 3 kilowatt system can easily be designed with almost 1 lakh 23-25,000, which you can self learn. If you visit our Hoshang Tech Center, you can learn how solar panels are connected. You can see how solar panels are manufactured. You can see how a total solar connection works, and you can replicate the same for your household purpose also, or for any commercial purpose. We will be happy to train you in all these things. And getting a hands-on experience in solar manufacturing, we are the only one a manual production line with where we manufacture panels right from cell testing, solar cell, tabbing, stringing, busing, everything. Each process is done manually. Only we have machineries for lamination. We have machineries to test the solar panels almost for 16 parameters. We have the testing machine for solar panels, and we have the framing machine. Machine is important for fitting the frame properly, so that no stress must be developed in the solar panel. And also talking about the testing, we test the solar panel for almost 16 parameters. So they consist of open voltages, it consists of open circuit current, short circuit current. These are major factors which we do. We calculate the resistance of wire, we calculate the field, cell efficiency. There are various all other factors where we test a solar panel at certain temperature and certain atmospheric pressure, that is 1 atmospheric pressure. Also talking about the lamination, we have a manual laminator, a semi automatic laminator, let's say. The laminator he is heated up almost up to 130 degrees Celsius. Then a sandwich of panel is slowly laid panel, and then it is laminated at a vacuum pressure. A vacuum pressure is applied. A vacuum pressure is almost of 60 Hg. Vacuum pressure different stages, almost up to 20 minutes. So a 20-minute cycle, a solar panel is properly laminated, and it is environmentally cooled at almost or normal environment temperature, 23-24 degrees Celsius, where it solidifies properly, and all the, let's say, EVA. EVA is a ethyl vinyl acetate. It is a chemical compound used for adhesive purpose. It is used for adhesive purpose in the solar panel. It is a thin sheet, inside the solar cell structure, which are delicately interconnected by bus bar purposes. Is my voice coming to you? Am I audible?
Yes, yes.
Okay. I sorry, I got a call. I'm using mic from another device. So sorry. Okay. So this is all about the solar manufacturing thing. So another thing is while designing this roof structure, this building is also, you can see it is connected with another building structure. So let us design. This is a flat roofed structure, right? So what we'll do, we'll design a flat roof for the other adjacent structure. While you visit physically, you must have to get these dimensions in meters. For calculating, you can use either a manual tape, or nowadays we have laser length meters. So they use laser and infrared to calculate the length of the building. So easily you can calculate the diagram, and you can have a rough layout of any obstructions are there or not. So you remember for this building we have set up an height of 15 meters, and this for this building the height is almost of 8 meters. We will check it into 3D view, but yes, the height has come up here. Okay. Now our task is to design this shade type of thing. Okay, this is the sloped roof. For sloped roof, we have to draw a face shift tool. Then we have to connect it edges. You need to move this its edges. Again, we will set its base height to 8 meters. Okay, let us check it into 3D view. Base height is 15, and okay, so now it is matched properly. In the same way, let us design a draw shift for. Always we have to first initiate with the available point, so that the system knows the proper length, and you will not have any sort of error in your design. So almost I'm having these 3 defined points. Okay, so I'm just using the length 6.5. Now this has identified the roof in the different angle. Change the angle. Okay. Okay, so our building design is perfect, right? Definitely, I have chosen this building is we can easily see how the building shadow. If you see north direction is this side, south direction is this side, east and west. So maximum number of our task is to install maximum number of panels on this roof. Then we have to leave over here and have some table installed here, and we have to utilize this slope area, and also we have to utilize this side slope area, which is almost at most opposite, but we have to install some less panels, so that we have let me again go to the 2D view. Okay, so first thing is to have the module add a sub array as per system suggestion. this is what how the system has designed: north side up, south side down. If I show you in the 3D view, it will look like, but this is not the feasible solution, so we have to make it properly. So then what we have to do, we have sub array, and then we have to select the solar panels which we need. Now currently the system has selected 315 watt panels, so we'll do is 335 watt panels, minimum and maximum. You have almost all watts of solar panels into this list. Okay, 235 watt, you see 175 watts, this is the name of the company, 185 watt, 195 watt, okay, 10 watt. Almost you have all the listed wattages of the companies where you directly can get a data sheet. You have 305 watts also. And this depends on actual available space, whatever watt panels you need to utilize, you need to connect, and also it depends on the inverter which you are using. There are some inverters are specifically designed for higher utilization of current, where you have a maximum input voltage of 110 volts, and maximum current will be almost up to 45 to 65 amps of current. Amps of current I'm speaking about. So while designing that type of panel, so you need to connect such panels into series, some panels into parallel. So you need to get this odd type of solar panels. Solar panels from almost 80 watts, you have a specified solar panels, let's say 100, 150, 185, then 200, 250, 300, 335. 335 is normally used solar panel. Then you have 450, 50, 650, and now latest technology, if we say, we have 720 watt solar panel. So these things have time get upgraded. So you have all these all type of solar panels to run almost all combinations, and required number of space you can complete. So let me install 335 watt solar panels. Okay, let me search them. Vari has 335 watt solar panel. Okay, and also Polycab, Adani. These are some of the reputed companies. Nova Solar is also a reputed company. Let us select 335 watt panels of Vari. Then the rack type of structure, which type of metal structure you are going to use. This is fixed tilt mount they have selected. But what we'll do is we will use a flush mount structure, so that it will be properly fixed to the directly fixed to the roof structure via clamping bolts. Okay, you will not have the panel. Then this comes to tilt structure of the tilt is defining the available roof, which we cannot change. This is the solar panel angle. So while flush mounting is the thing where you will place the angle in such direction as of roof structure, roof design, roof angle. So access to change the solar panel design. Also, just one thing you can change is table spacing and rows, columns. These things you can change, but later on we'll see how many number of panels we can install. Okay, and then we will decide the available space. Okay, available space, mounting height, module spacing, row spacing, all these things we can change later on. So I'll just first, after hitting update, we see that system has installed so many panels into this total row. So let's say to have an optimal generation, system has put on 56 panels, and which is coming up to 17.53 watt, and solar panels are of 335 watt, right? So 17. So let's say we will need some space from the above. We will need some walking distance from. We will need some walkway from middle, like our structure, our college structure, and also we'll need a handrail from lower side. So one thing, one after another, we'll try to design other structures inside. So first we'll select the handrail, and we will select the topmost two sides. Okay, core height we will keep it as 1 meter. The major disadvantage of this software is that you have to put all this length in a meter format, not into a mm or not into feet. It generally knows all these distances into meter. Okay, so this is the handrail, how it will look. So this height is almost of 1 meter, which is the safety point of view better for all these things. The next thing we need is roof access. We can have it from any other side, or we can have it directly temporary from this side, and you can lift all the solar panels. There's one thing you have to keep in mind all the parameters, all the things while installation, whatever you will need. Each panel weight goes up to 45 kgs, more than 35 to 45 kgs. So sort of panels, you have to lift it properly, you have to place them properly. So these things you have to keep in mind. Okay, so while designing such thing, let us now move towards panel design and table. Okay, if you see total panels which we have are 56. So 56 panels into 335. What let me do? It is almost a 18 kilowatt installed, right? And here it shows 17 kilowatt. So based on the inverter, what we will do is we will have a table of almost 10 panels, 20 panels each on this roof space, and let us see if it works out. Why I am saying number of panels 20 is each panel of a 335 watt has its normal operational voltage up to 38 volts. So when we multiply 38 into 20, you get an optimal voltage of 760 volts. So which is the minimum working voltage for solar inverter, right? So while designing, while having such type of tables, or you can decrease it to 9 also, 18 panels, 9 a table of 9 panels each. When you connect two tables into series, it will be 18 panel string, right? So you have to change the string. You have to come when you need to completely change some things into a singular. We have not created tables in this structure. So when you create a table, you will have the table option, so you can have some changes into table. But when you have to make changes in the totally this structure, you have to have a sub array you selected, and then you have to have uh, 2 rows, 5 columns. The distance will be portrait. Mount height is almost of 0.1 meter. It is okay. Vertical spacing, we can increase it later. Just we will hit update first. Okay, just we will hit update first, and when we will select a table, so this will be the table, it will be selected. Okay, so 1 2 3 4 5 and 2 rows, right? Table selected. Now what thing we can do is we can increase the table height. Okay, so we have to again select a sub array, and we have to increase the mount height, vertical module spacing, row spacing. We have to increase it to 0.1, 0.4, right? So far, because we are not independently having the space below and above also, so it is directly, the system is removing a single table. Okay, so just we have to increase the table spacing by almost less quantity, less number. So let me try it. Okay, so we have a proper space. We can also increase it further. While selecting the table, you have the total module count, and also you have the total length, length of the table, which is 4 meters, and 5 width. Okay, so this way you will have 4 meters, 4.9, and this will be 5 meters properly. This will be 4 meters and this will be 5 meters of length. The length of solar panels is almost 998 mm, which comes to almost 1 meter. So this will be of 5 meters, and height of the panel is almost of 2 meters, which comes to in mm it is 1986. It is the glass size, so you can add up to almost 4 mm, 2 mm's let's say expansion gap. So it comes to almost 2 meters, and this 2 meter and this 2 meter, this, so 4 meters will be the height and 5 meters will be the length of solar panels, according to which you have to design the structure. You have to design the holes of solar panels, you have to match the holes of solar panels. There will be a rafter and purlin. Rafter is what is connected with solar panels in the between, and purlin which holds this rafter and directly connects the ground. These two things are almost useful for solar panels and solar structure. If we again go to a 3D view, you will see, you will have this thing this way. So one thing we can see is 1 meter length for such type of structure will have a shadow on solar panels. So to look if the panels are shadow free or shadow, there will be a shadow on. What we'll do is we will save our design once. Okay, let the design be saved. And when you save the designs, you have the sun path simulator over here. So when you turn on, and here you have days, month and time. And currently if we go to November, okay, today is 26/11. Okay, 26/11, and time if I start playing, north side direction you see how it is, south side direction you see how it is. So you have a total solar axis. You see there will be almost available, and in the evening section there will be no let's say uh, roof shadows available on this thing. No shadows directly by the railings you are unable to any shadow from the solar. One thing is we are having shadow from this side over the panels, and the solar axis. The sun is coming from the east side, and also then it is setting in the west. You can check the solar axis for any month and any time of wave. So this is the shadow which will be coming from the railings on the solar panels. So there is also a disadvantage with solar panels when you have a full cell type of solar. Solar panels are of almost manufacture. If the construction, if you see of two types, bifacial panels you see, and also a solar panel consisting of almost 72 cells directly connected. So if there is shadow on a single solar cell, let's say if a solar panel has total 72 cells, all the 72 cells are connected in series with each other. Okay, so when you have 72 cells connected in series with each other, and let's the three cells, no, six cells from below are covered into shadow, then the current being generated from the solar panel drops. So each design when you do, you have to be almost shadow free. So for this design we will almost once check what is the issue, and we will decrease this height of railing up to half a meter. Okay, so when you make changes in this design tool, you always have to click it updates into design. Okay, then we will have then again we will save the design, and then go to solar sun path simulator. We will go to third angle, and then we will check if our design is shadow free or not. Six, 9, this is in the afternoon. 12, this is 3 in the evening, and this is 6. So we have successfully designed a shadow free design. You have minimal at 9 a.m. early morning 9 you will have, because this is the east side. Okay, so early morning 9 we will have somewhat so thoda solar thoda shadow on the solar panels, and then it will drop. So this is for almost April month. Then we will go to June, July. There is no almost it rains so far. Then we will go to November and December, and you can check it for 9 you have a lot more, then 12 and 3. 6 to 9 you will have somewhat solar shadow, then the design will be completely free. So this is not about only one building. You can also check for other buildings too. Are they shadow free or not? See that the shadow from these solar panels is being deployed on this, and this you the this structure solar height is not so defined, but this will be completely darkened. The total string being generated will have less power. So if a single panel in open sunlight generates let's say 9 amps of current, if a single cell is covered, it will drop up to 5 amps. So there will be a major difference of 4 amps, and 4 amps from a single panel or 3 panels will reflect into major losses in solar generation. So which is the disadvantages of using 335 watt panels. Greater on using of 550 watt panels, there are two panels connected in parallel. So the thing is, if half of the side of solar panel has a shadow, then another half keeps on generating at its full power. So this advantage we get into bifacial panels in that way. This is the one building, and another building if you see here, you see the shadow analysis. While designing and using solar labs, you must have an accurate height of the building and also accurate heights of all other obstructions. Let's say side building, you have to calculate the height. It is everything needed to height. So this height is also needed. This is a lift thing, but we have all up to designed just at the top side. Okay, so when you have properly heights defined into a design, then you can easily calculate accurate shadow analysis for all these things, and also the trees. If you have properly the height of the trees, then you can calculate. Here you see this side. Okay, this is one thing where you can have a solar path simulation in this software. Another thing we can do is, let me save this design again. Another part we can do is heat access. So whichever solar panels are properly having heat access, or these designs will be shadow free. So let us close this thing and see if we have these options in this thing. This map shows us the endurance. So these are easily reflected. It shows the heat dissipation on the solar panels, how it will be dissipated. Another thing we have here is solar access. Yes. So here we can see the solar access for each panels. So all other panels which we have designed are completely shadow free. Some of the panels you see have a different color. Some here panels, if you see, you have different color, but at most panels which we have generated are shadow free. Here if you see, some of the panels will be have less shadow, and here we have some panels which will be almost have heavy shadows, because this is almost north direction. East will be this side and west will be this side, so there are heavy chances of being losses in this panel. So we can either delete this panel directly, or we can change it, optimize it to other available space. This is how the heat map it shows. This is a single table. This is string 1, this is string 2, this is string 3, and this is string 4. Each panel has a length of 1 meter by 2 meter in length. So this becomes to 4 meter, and this becomes to 5 meter. Okay. Any doubts or questions you have? Okay. So let us design further for this available space also, and can do this thing. So system has by default it has set up north south direction. So now what we will do is select right click, then we will select a sub array, then we will select the solar panel wattage is to 335 watt. Then we will have the fixed tilt mount structure. Okay, by default we will have a TPSSL 4 single leg structure, two leg structure. These are different types of structures. So I'll show another. This is 4 single leg structure. Okay, and the direction what we'll do is we'll have it as north side is up, south side is down. Okay, so we'll have it as at southwest direction. Building has its own way that way, and we just will click update, and we'll see if more panels can be stacked up together. Let us spacing or module spacing if system has selected so far or not. Modules spacing we can table spacing we can reduce it almost to uh, so somewhat more panels can be fitted up. Okay, then another thing we can do is have a table of 4 by 2. Okay, so this can be the structure. Next thing is if we see in 3D view, we will have single leg structure how it looks like, because the mount height is more I guess, so it is not showing us the proper structure. This is 4 mm 2 leg structure designed for a single 4 type of panels. Okay, then we will change the solar structure for 4 leg structure. This is the ballast type. So we have to change now the ground height to know. This is different type of structure which you can use. Okay, this has 4 legs for each panel. On flat roofs or flat ground structures, you can use this type of structures. While fixing this type of structures, you have to clean the lower surface properly. Then you have to put up an anchor bolt of almost 3 inches into the roof. Then you have to mix waterproofing cement in your concrete, and then you have to make a proper mold having its leg properly aligned with all other legs properly aligned, and then you have to fix the rafter and purlin. These 2 things. Now we can move to another type of structure. We will increase the mount height to half a meter. No, more than half meter we will need. This is type 2. So let us try another structure. This is elevated structure, and here also we will have mount height up to 3 meters. Right? Update. Let it update. And let us go to third angle. So this is what we prefer, a proper designed truss at 20 degrees of angle, and then have we can utilize the lower space of area for several purposes. And the number of panels have also increased. So for time being, we have to fix the structure with fixed tilt, and it has to be a default fixed structure. We have to update the design, see if the structure is proper or not. We have to decrease the mount height a little bit. Yes, okay. So this height is up to 2 meters, so you can easily go below and check the wiring connections and everything. So this way you can have some panels connected to the roof, and also some panels connected to the uh, roof ground structure also. As I have said earlier, if we get the available space, let's say this side, then to get a proper estimate or approximate estimate, what we'll do is we'll have a flat roofed model just directly from this to have a rough estimate. If we can if we can successfully install and see you get 200 kilowatt of installation in it or not. Okay, so once you select the area, we will keep the height up to base height at 3 meters, which will look like this. Okay, a simple foundation type of thing. Then what we'll do, we will have a module, we will add a sub array. Okay. So the thing is, we are increasing the total DC project more than its limit. So it is not permitting us to install more than 200 kilowatt. We have almost installed, here you can see 199 kilowatt on all the available total buildings. So we are at most successful in achieving 200 kilowatt. So rest 50 kilowatt we can utilize this roof, or we can utilize these two buildings, these two or three buildings for optimal generation. Rest some of the panels, remaining panels, we can try to install it here, or we can upgrade some building, some panels from this building, remaining buildings to 550, 650 watt, and try various permutation combinations to have an optimal design. So another thing, as we have a total generation of let's say 199 kilowatt. So we will attach an solar inverter. We will first save the design. We will have a solar inverter which comes into string inverter. We'll have a maximum limit of 200 kilowatt. And here we will search for grow watt. Grow watt 30, 50, 2 kilowatt. $200 and next 200. Okay, so grow watt 200 is not updated in this solar website. So we will have a 100 kilowatt inverter, two inverters of 100 kilowatt, which we can make them parallel and supply it to the grid. This is grow watt max 100 LT. So thus one grid inverter, we will install it in the central building so that all other strings can be connected properly. And again one inverter we can install it at this building. This is a rough estimate to have a solar inverters. So while we design an actual design, you have to combinely find a closest space to the available net meter or the available roof where the MSEDCL supply has come, and total things we have to connect it to so far closely connected. The DC side has to be length has to be so less as less as possible, and the AC supply we can take it up to 100 to 200 meters. So while talking about 200 kilowatt, let's say our panels are of 315 or 335 watt panels. So total 623 panels we have installed. So AC size is up at the most 200 kilowatt, the upper limit, and DC size is 199 kilowatt. Okay, the total two grid tied inverters we have, and this is the ratio which is available, which will be possible. So once when we save the design, then we get the option to generate and calculate the solar generation, which will be done into solar panel, into our solar system. So when we click on solar generation or calculate generation, we will have its annual generation, we will have its specification generation, we will have its performance ratio, and we will have its energy offset. Yes. So almost we will have 277 megawatt hour of power. Specific generation we will have is daily generation we will have almost 1300 units. Performance ratio is nice, almost up to 75%. The thing is, while designing the solar plants, the angle if you see is also not so good and properly designed, north side up south side. So this building is almost uh, useful for us. So these things will generate in the early morning section because the sun rises from east, but in the west side when sun sets, this generation will stop up to the degradation of solar intensity will start by 2 p.m. to 3 or 3:30 p.m. So we won't have a lot more generation in the evening period of all these side panels. But the thing is, almost we are having so many panels installed on the land surface. So these panels have also been contributed in total generation, so which is helpful for us. So when we have the total generation, we can go to home page. We can have a total generation report of the solar plant, residential plant. And as we have seen, the performance ratio, specific generation of daily generation, you can see total last modified date, you can see total generation graph, you can see. Then another thing is a loss analysis. You can see a total loss, how much it will be there. Bill of material, handrails of how many meters you will need. Modules of 335 watt, how many you will need. Modules of 340 watt, how many you will need. Modules of mono 335 watt, how many you will need. So whatever you have used in your design, so a bill of material easily you can generate. Next thing is battery. This is an on-grid system, so no need of battery. Other financing and pricing issues you can add, and you can easily document your proposal from this Solar Lab software. Okay, you can also have a 3D video. So that option, let me see where it is. You can also directly share a web proposal and have a 3D video. Let me see if that option is here or not. To view 3D model, you have to scan this QR code, which will take you to the official site of Archive 360 and show you the 3D model, how a proper video it will look like. So now I can show you the inverter specifications of our 240 kilowatt solar system, which is our college system, which is currently running, currently generating. So I'll be happy to share our solar specs of our 200 kilowatt. So let us search for Shine. So now currently I am trying to log in into our inverters of our college. This is the plant monitoring system given by Growatt company. So total megawatt which we have, total power generated from a single inverter, if we see, generation today, if we see, is total generation of our plant, let's say from last year, if you see, is almost of 328 megawatt hour units. 328 megawatt hour units we have generated from our solar system, including all this 100 kilowatt for almost 2 months, then 200 kilowatts for almost 2 months, and then we have upgraded to 40 kilowatt. We have upgraded to its ultimate peak limit. Okay, so togetherly it consists of 240 kilowatt of a total plant. Here you have to see 798 units generated today. As it is a winter season, so today the climate is almost a little cloudy type of thing. So we had a less generation up to the mark. But daily, if we see, we have daily graph. If you see, we have almost 815, 883, 834. This is 23rd of September, November. November, it is 855. You have daily generation 918. Then this is of September, 960, 949. So this keeps on changing year on year. So if we calculate for year, then we will have at most 2000 units, 2143, 21,000 units being generated in September month, which is almost the 70% of units we consume as an engineering college. So here is some of graph of the generation. Total revenue we haven't added because of the changing tariffs according to the MSCDCL, because sometimes MSCDCL provides us energy by 17 rupees, sometimes by 17.3, 17.4. Fuel charges keeps on changing, rest other charges keeps on changing. So we haven't added the total revenue thing. Currently 50 kilowatt power is being generated. Now the time is almost 4:30. So the solar intensity at most less in the power, but the west facing of our college, this is the north side, this is the south side. This way, here we have east side, and this side we have west side. So panels installed on this side and this side, this total panels, and these panels are almost generating 70% and 30% power from the north south slope panels. So togetherly now they are generating 50 kilowatt of panels. Here you have deforestation, and here you have CO2 emissions. So these emissions, this number helps us to gain the carbon credit and save us a lot more taxes for our college energy audit. Operational days we get, the devices, we total devices means the total inverter capacities of we get. Individually inverter capacities also we have, we can get the total specs of each inverter. It is connected properly. These are two inverters, each of 100 kilowatt. Rated power is 100 kilowatt, but we can almost take it up to 120 kilowatt. Generation of units you can calculate 420. This inverter is inverter 1 installed on A wing and B wing. This is the another inverter. Okay, this is the another inverter which has generated almost 398 units. While yesterday's lecture I spoke about that a single kilowatt, 1 kilowatt, 1000 watt panels, when you put it into sun, 3 units have been generated. So when we have 100 kilowatt, 420, if we divide it by 3, we have 140 units. The thing is, per kilowatt, 4.2 units have been generated. The minimum of for 100 kilowatt, for 1 kilowatt, 3 units are generated. Then for 100 kilowatt, 300 units have to be generated. But if we see at our current statistics, 420 kilowatts have been 420 units have been generated. Because of the 120 units, Per watt, per kilo, per 1000, per 1 kilowatt, if you say 4.2 units have been generated. So this shows us a very useful data coming out of our solar system. You also have a data logger statistics. So one of our data logger, this data logger is GPRS, so it has SIM based. So this has SIM, so it sends the data to cloud, and then the data comes to us. Another one is Wi-Fi based, so it is connected to our college grid, Wi-Fi grid, and then it sends the data to cloud, and then the data comes to us. This is ELC meter, so it shows us the consumption. We had used it for just for 100 kilowatt purpose in the initial days. The thing is, while using at heavy electrical supplies, calculating the current at very microsecond becomes difficult, and we had some issue with maximum, because the net meter was not installed, and zero export function for such a huge college was a little risky, so we haven't used it so far. You can also see the generation graph. The generation starts at up to 6:30 a.m. and it is currently going on up to 16:05. So after half an hour, the data keeps on updating, and current power you will see at almost 3 to 4 seconds being updated. You have other warnings and everything through this solar inverter thing. So this is all about the Solar Labs software, and also these are some of the specs of our solar 200 kilowatt solar plant. I can also have the generation statistics for our 100 kilowatt, which is installed for our Garda hospital, which generates almost more than 350 400 units per day. So if you wish, I can log in and show it to you. Do you want to see the statistics for Garada hospital? Okay, so let me log out from here. Total power, these are all the statistics for Garda hospital. Total power of 200 megawatt hour units we have generated. Total today's generation is almost of 317 units, 317 units. This month we have generated total energy, total units, that is 8,300 units. And this is the graph of monthly usage for November month. You can change it to October. Okay, you have the graph line of October. This is 342, 346. You have 406 units generated in the October, and total, if we see in 2023 we had 1 lakh units, and currently we have generated 89,000 units from Garda hospital from a 100 kilowatt solar plant which has mono type of solar panels manufactured at our own facility, almost 300 panels installed, and a single grow-watt inverter of 100 kilowatt each. Currently, it is a ground-mounted structure, so you can see the difference what a roof-mounted structure has benefit and what a ground-mounted structure has a disadvantage. As the structure is ground-mounted, we get the shadow from all other sides, and the generation is up to 13 kilowatt, the current power generation. And if we see for a solar rooftop of our college, we are having 50 kilowatt of generation. So 50 kilowatt of generation for an 1 hour time span will be 50 units, right? So these 50 units can be used for used at various minimal purposes like solar street, like street lights, like the as our college is daytime running, so these 50 units can be very useful for keeping some lights in on position for night lamps, you can say. Some light units can be used for hostel purposes, but in ground mounted structure, as soon as the time becomes 4:30, 4:35, the current power reduces. So this is a major thing where you see where you see the shadow design for this thing for current power. Then you can see the deforestation, how many carbon emissions we have used, and devices. If you have a single device here. We have single device inverter list data logger. We have a single data logger and another data logger. This is from another plant. This is just a 10 kilowatt. We have kept it for demonstration purpose. This is the single device used for Garda Hospital. This is VH. This is a 10 kilowatt solar system installed in Nashik school, where a 1000 square feet area, a school completely built of disposable solar panels, means the solar panels which have crossed their lifespan up to 35 years. So post 35 years, we have procured solar panels by 5 rupees per watt, and we have built a school out of it, completely covered by glass. And this glass type of thing, solar panels, we have connected to their grid type of structure, and which has generated today a power of 21 units. You can see that solar panels, 35-year-old solar panels, multi is the solar cell structure which we have used. So it has generated almost 21 units per day, and this month the total generation of that solar hall, we say, which is been constructed in Nashik, it has this month generated 610 units. So a 35-year-old solar panel also, the 10 kilowatt means almost 40 panels have been installed, and the roof, which have completely been sealed, and all the walls and roof are being constructed with solar panels, which are degraded solar panels, of which we have used BLDC fans for less energy consumption and ventilation. We have, as the solar panels get heat up in the solar, so we have used exhaust fans which also run on solar panel, and the generated solar panels power is directly being utilized by the kids for their PCs and small equipments being used in the solar hall. So these are all the statistics for the Garda Hospital, and this another plant is for just the data logger. We have installed it for the monitoring purpose. Rather creating a separate login ID, we have attached the data logger here. When we will delete it from here, we will have the accurate data for solar our solar plant also. So this is all about the solar labs and also our current solar statistic data. Okay, so if you have any sort of questions or any doubts, you can please ask. Yes, sir. If anyone wants to learn the solar software for trial purpose, then I'll be happy to share the login ID and password for a day or so, so that you can try several designs. The thing is, you have to update the software with almost the basic available plan with the Solar Labs. Currently, we are not running any internship batches, or else we would have updated it. The total cost we had for the Solar Lab software was almost 78,000 for an year subscription. But just to renew a standard package will cost you almost 1200 rupees, and it will have you almost 1500 credits. So you can select the area and try to design it for yourself, or if you need any type of guidance, then you can happily contact us. Thank you, sir. Thank you, sir. Okay, sir.